The second section of the periodic table really is how the periodic table shows us trends. And I am going to warn you on this that this is something that mostly doesn't come inherently to you. So you really do need to study this. You need to read it in your book. And you might have to go over it a couple times for it to really make sense. If not, this can be a really tricky section. And you probably won't like the way your grade looks when you're done with it. So just keep that in mind that, this is new. This isn't something you're, innately born with, so it's expected that you're going to work for it. Couple of things here. When we say the properties are periodic, that means that they periodically repeat. So when we have a periodic table, it indicates that there is trends being shown. The way an element acts and the way it's positioned on the periodic table are a direct result of its electron configurations. So the way the electrons are laid out in the atom drastically affect the way that the atom's going to act. The outermost electrons, or the valence, are the most important, and they're going to have the largest effect on what we're doing. Changing an inner electron, like a D or an F, is going to do markedly less than if you change an S or a P on the outside. So just keep in mind, like the ones further from the nucleus generally have, they're much easier to take and give. And then what you want to remember is the shielding effect. So shielding effect has to do with how far you are from the nucleus. If you're right next to the nucleus and you're an electron, then you really feel that nucleus. So you really feel the pull in. As you move further and further away, you're just getting further away from the nucleus, but the bigger thing here is other electrons are getting in your way. So it's just like if, if you're in the front of the class, you can see the teacher, and you're the first one, and there's no one blocking you. If you're in the back of the class, there are people in your way, and they're shielding you from that interaction. And the same thing happens for electrons. So as you move down the periodic table, as you get further away from the nucleus, each level has a certain shielding effect, and that will come into play. So the first trend we're going to look at is atomic radius, and atomic radius deals with how far atoms are from each other. So basically, what's half the distance from nuclei to nuclei? And as you can guess, an atom's pretty small. So your units are going to be nanometers, they're going to be angstroms, or picometers, which are all very small. The biggest trend is up and down. So if you look down here, your group trend is when you're at the top. So like think hydrogen, helium, you're going to be very small. And when you're at the bottom of the periodic table, you're going to be very large. So that's probably your biggest trend for atomic radius that you worry about. When you're looking at the period trend, it's a little harder, and the period trend has to do with that shielding effect. But when you look on the left side, you're actually larger. And when you're on the right side, you're generally smaller. And what this has to do with the fact is that as you start on the left here, you have a certain amount of shielding effect. And the whole row has the same shielding effect because you're the same distance from the nucleus. And as you go across, you add more and more, one more electron, one more proton, one more electron, one more proton. And what happens is your shielding effect is exactly the same. So what happens is you start getting more and more protons, and those protons start pulling you in tighter like a belt. They kind of cinch the waist in. This is far less dramatic than the up and the down, but it is a trend that you have to watch. And if you look on our next slide here, you can see if you look at the top and you move down, you get drastically bigger. And if you look on the left and you move across, you're cinching your waist in, and you're getting smaller and smaller and smaller. And again, we're not saying there's never going to be an exception. We're not saying that this is, perfect in every way. But if we're looking for the trend, this is the trend. So if you're looking for very big atoms, you're looking for down and to the left. If you're looking for small atoms, you're looking up and to the right. Next one is about ions. So this is when things have charges, and we know that metals tend to lose electrons, which makes them smaller, and we call them cations. So what happens for ionic radius is when you're a metal, you get smaller because it's like you're losing weight, just like if you lose an electron. And again, you don't need to know that lithium was 1.52 angstroms, and now he's 0.6. But if I say which of these is smaller, you definitely want to know that lithium plus 1 is smaller. If I ask you which one's bigger, you would definitely want to know that lithium is bigger. And then again here, it's saying if you have the larger the positive charge, the smaller the radius. So like if I went to sodium plus 2, I would be even smaller than the 97. So like I went from 186 to 97. If I did another one, I would get even smaller here. But the big thing here is just to know that for metals, you're getting much smaller as you go. On the flip side, that means that nonmetals are getting much larger, and they're very because they're gaining, so they're becoming negative and they're getting larger. And if you look here, there's lots of examples. You don't have to write them all down, but if you look here, we have nitrogen, and then he gains 3 electrons, and you can see he gets much larger. And last thing for this section is just one thing you have to worry about is if you're just comparing like an element to its ion, that's okay, and you can do that simply. If you are doing something where you're comparing different ions of different elements, you cannot just do it based on a trend. So what you have to do then is you actually have to figure out how many protons you have and how many electrons you have, and you actually have to compare them. So you can see these are all different elements, and they have lots of different charges. And if you look here, what you're looking at is who has more protons here. So these all have the same actually electrons, so that's really simple here, same electrons. And what we're looking at is whoever has the most protons pull in would be the smallest. Whoever has the least protons pulling in is actually the biggest. So it's like a tug of war. Your protons are pulling you in, they're making you smaller, and your electrons are pulling you out. And this is if you're very close in electrons. If you're very different, like if I have 54 electrons and 10 electrons, then it's not as distinct. But if you're very close or isoelectronic, then you have to really refer to this to see who's bigger and who's smaller.